Hi guys, welcome to our first lecture on stoichiometry. And stoichiometry is all about ratios. So here we're going to talk about peanut butter and jelly sandwiches for just a minute and cooking. And that's because chemistry is like cooking. When you go to cook something or even do something as simple as make a peanut butter and jelly sandwich, you need to know the ratios of all of the different ingredients so you can make the product, the peanut butter and jelly sandwich or the cookies or whatever it might be, so you can make the product to come out the way that you want it to. And that's the same thing with chemistry. Only instead of having a recipe like you do with cooking, you end up with a balanced equation. And that balanced equation is what's going to tell us our ratios. So we're going to use stoichiometry for quite a few things. And I think you're going to find that you know how to do a lot of this. So it's going to be a pretty easy day for you. So stoichiometry is used for calculating the amounts of reactants or products that are involved in a reaction. It's also used to determine how much of something you have or need or can make given one other piece of information. So it's kind of like, again, if you're trying to make your peanut butter and jelly sandwiches and maybe you have some friends over and you go into your kitchen and you realize you have this really nice brand new container of peanut butter and you have a whole loaf of bread and you're thinking, I have this under control. I'm going to be able to make everybody a sandwich. Then you open up the fridge and you realize that the jelly is really lacking. There's only a tiny little bit left at the bottom, right? And so you have to figure out how many sandwiches can I actually make from this little tiny bit of jelly that's in this jar, right? That's what you use stoichiometry for. You use it to figure out how many sandwiches you can make given certain amounts of ingredients. So how do we do it? Well, obviously we don't do it in our kitchen, but instead we do it by looking at balanced equations. So balanced equations are like our recipes. The coefficients in the balanced equation tells us how much we need of each different ingredient. This unit is going to use a lot of old skills, so you're going to notice several things show up again. One of them is balanced equations, because all stoichiometry problems require a balanced equation because that is our recipe. So you will either be given a balanced equation or in some cases you might have to balance the equation yourself. We will still be using moles. Now we're going to add a new conversion factor with moles. That's what today is about. It will be called mole ratios. And we will still be setting up our problems using dimensional analysis, just like we did before with the boxes where you bring down the units and you do that as much as you need to, in order to scale up or down a reaction, just like you would scale up or down a recipe. You could cut it in half if you needed less. You could scale it up for a crowd. That's what stoichiometry lets us do. So what is this new conversion factor that lets us do that? It is called a mole ratio. And mole ratios come from balanced equations. So when you look at a balanced equation, what we didn't tell you earlier in the year is that those coefficients in your balanced equation, the 2 and then the invisible 1 and then this 2, the coefficients are actually moles. So when you have a balanced equation, you have the number of moles of each different compound that is required to make this reaction go. So here, if I had 2 moles, which are also like molecules, 2 moles of hydrogen and 1 mole or molecule of oxygen, I could use that information to figure out how many moles or molecules of water I could make. Just like you could use how many slices of bread you have, how many spoons of peanut butter you have, how much jelly you have to figure out how many sandwiches you can make. So these mole ratios from the balanced equation, these are the magical key to stoichiometry because they let us compare all of the different compounds in our recipe, our balanced equation. So I can start to tell, well, what if I have 3 moles of something? Then how many can I make? What if I only have 2.5 moles of something? Then how many can I make? So this mole ratio is going to let us answer a lot of questions about what's going to happen with our chemical reactions. So what does a mole ratio look like? Well, it looks like a conversion factor. So I've given you 3 conversion factors here on this board. These are the 3 conversion factors that go with this balanced equation. And so what I want you to see is that I have compared these 2 reactants to each other, right? 2 moles of hydrogen, 1 mole of oxygen. I have compared hydrogen to water, right? So that's the 2 moles of hydrogen and 2 moles of water. And I've compared oxygen to water, 1 mole of oxygen for every 2 moles of hydrogen. So I made these different conversion factors, these mole ratios, just by comparing 2 things straight out of my chemical equation there. And notice this little note down here, it says, do not reduce your mole ratios. If your mole ratio is 2 to 2 in the balanced equation, you keep it 2 to 2. Okay, don't undo that, don't simplify it, because this is important because there's other moving parts in the equation. So don't reduce your mole ratios. All right, so the other thing you need to know is that mole ratios can be flipped. So this top row here, these are the ones that were on the previous slide. Okay. How do you know which one goes on top and bottom? Like, did I just make that up? Well, I did, but that's because it doesn't matter if I'm not using them in a problem which one goes on top and bottom. I could have just as easily flipped them over the other way, and as long as they came from the balanced equation, they would be perfectly legitimate conversion factors. So how am I going to know which one of all of these I should be using? Well, we're going to do dimensional analysis. So we're not going to worry so much about what goes on top and bottom. We're going to set up our problems. So if I put, let's say, moles of O2 was in my given, right? When I bring this down and I write the word moles of O2 on the bottom, it's automatically going to be letting me know that I'm either using this or I'm using this, because I have to bring those units down. Now, how am I going to know which one of these to use? Well, it depends on what they're asking me about. If they want me to tell them about hydrogen, I'll use the top one. If they want me to tell them about water, I'll use the bottom one. So we're not going to worry about all of them at once. We're going to follow the steps that we've learned. Write down the given, bring down the units. It's automatically going to help us build the specific ratio that we need. So here I've got, now you try. How many mole ratios can you make from this equation? Okay, I'm going to tell you that it's a lot. I would pause this if I was at home doing this, because I'm going to pause it at school, and I would write down all of the different combinations that you can make. Once you've tried on your own, then I would unpause it and hear the explanation. So if you have already tried, now I'm going to walk you through it. So what I'm going to do is I'm going to take this magnesium. Let me balance my equation real quick there. I'm going to take this magnesium and I am going to compare it to everything else in the equation. So for every 1 mole of magnesium, it looks like I can make 2 HCl's. Okay, I can also compare magnesium to magnesium chloride. So that's going to give me another option. Magnesium, and then that looks like 1 mole MgCl2. And then I can also compare it all the way over here to the hydrogen, so that's another one. So my little lines are in the way there. 1 mole of H2. So this compared magnesium to everything else in the equation. But there's more than that I can do. I can also look at hydrochloric acid. Now I've already compared these two, right? I did it right here. So I'm going to now compare HCl. So I'll say 2 moles of HCl. I'm going to compare it to, oops, here we go, 1 mole of MgCl2. And then I will also compare it to the hydrogen, just like I did on the top. So get 2 moles of HCl for 1 mole of hydrogen. Okay, so now I've compared this guy, I've paired this guy. Now I'm going to come over here and I'm going to look at my product side. On my product side, I can compare these two. I haven't done that yet. I'm just going to squeeze it in right here. 1 mole of MgCl2 for every 1 mole of H2. Okay, I've already compared MgCl2 to the two reactants. So I can make 6 different mole ratios from this equation, but I can also flip them upside down, and if I flip them all upside down, I'd get 6 more. So I could actually have 12 different mole ratios. So if you wrote any of these upside down, they're totally okay because I can flip all of these upside down. Now, the good news is we're only going to need one of these per problem. We are not going to have to write out all 6 or 12 of them every single time because our dimensional analysis approach will give us the one that we need. So let's try a few so you can see how these work, and then we'll do some practice. So here I've got a combustion problem for us, and here is the question. It says how many moles of carbon dioxide, so I'm going to write this up here because this is what I'm looking for, can be made from 19.6 moles of oxygen gas. I like to write that up here so I can tell what I'm doing. So I'm trying to take these moles of O2 and turn them into these moles of CO2. We're going to follow the same steps we learned earlier in the year. So write down the given, 19.6 moles O2. Okay, step 1, right? Remember that step 2 is always to bring down the units. So these are my units. They have to come down. That's not optional. It's an absolute must. So just the words come down, moles of O2. Okay. Now I need to complete my conversion by putting something up here on top. Well, right now we're working with nothing but mole ratios on this one, and we can take moles of A, which is any compound, and we can change it to moles of B, which is any other compound, as long as we have a balanced equation, which we do. So I'm just going to pick a different compound. I'm going to put A with B. Well, I put A, oxygen, on the bottom, so I'm going to put the other thing I care about, which is CO2, on top. I need to plug in my numbers. The numbers come from the balanced equation. So from the balanced equation, I'm going to take this 5 and put it with the O2, and I'm going to take this 4 and I'm going to put it with the CO2. Now, math, multiply across the top, divide by the bottom. So 19.6 times 4 divided by 3. Okay. So 19.6 times 4 divided by, that's a 5, not a 3. Sorry, guys. It's hard to talk, write, and punch things in the calculator all at the same time. So that gives me on the calculator 15.68. But notice I have to have units and sig figs. So sig figs come from the problem. There's 3 sig figs. I'm going to keep these 3, look at the neighbor to decide if I should round up. Looks like I should. So 15.7, and then my units are the ones that didn't cancel out, so moles of CO2. This is my final answer. Okay. And for today, the big new thing was this right here. This is a mole ratio. It allows us to compare any two things in our balanced equation. Let's try another one. All right, so if you make 13.2 moles of water, how many moles of oxygen did you start with? All right, so I'm going to take this information right out of my problem and I'm just going to stick it up here. You don't have to do this step, but this is what I like to do. Moles of oxygen. So I can tell where I'm going and when I need to stop. Okay, so I'm going to start with the given. That's the 13.2 moles of water. I'm going to bring these units down, moles of water, and then I'm going to change them to something else. I'm going to change them to oxygen. moles of oxygen using, right, my mole ratio. The numbers are going to come right out of the balanced equation. So that's a 5 and that's a 2. So again, we multiply across the top and we divide by the bottom. Now this one's interesting because my calculator gave me 33 exactly, but for sig figs, I need 1, 2, 3 numbers. The way I fix that is I just add a 0.0 to the end. Okay. This would be moles of O2. Again, the big new thing for today is this one thing right here, which is our mole ratio from the balanced equation. Now, what if I don't want moles? Then what do I do? Well, you don't do anything different, right? You just pull back in the things that you already know. Okay? What we did today was we added the ability to switch from compound A to compound B, which is what you see in this very top line. It looks like I left out the number sign here. So this was our new conversion for today. Moles of A or moles of B from the balanced equation. But if we don't want our answer to be in moles, it's not a big deal because we know how to change moles of anything into grams of that same thing by using our periodic table. We're not going to actually be doing molecules today, so we'll mostly just be doing these. Okay, so the important thing to realize here is that this mole ratio is what allows us to compare different compounds. If I need to compare different compounds, I have to have a mole ratio to do that. Then I can always change it into like grams or molecules if I need to, but the mole ratio is the magical thing that lets us switch compounds mid-problem. So we'll do one more, and then we're going to practice some independently. So again, the same equation from before, only now what I want you to notice is that we're starting with the moles of water. So let me write that down. Only this time, instead of asking about moles of oxygen, it's actually asking about grams of oxygen. So it's a little different, okay? But that shouldn't matter to us because we know that we can take moles of any two things from a balanced equation and put them together to switch compounds. And we also know that we can always look up the weight of 1 mole of anything by simply using the periodic table. So even though this problem looks different, our approach is going to be the same. We are going to write down the given, which is 76.4 moles of water. We are going to bring these units down, just the words, not the numbers, moles of H2O. Okay. Now we need to put something on top. So today we're sticking to these two ideas, right? So we want grams of oxygen, but putting moles of water and grams of oxygen is not something we're allowed to do here, right? If I have moles of water, I can change it to grams of water, or I can change it to moles of something else. I want something else. I want oxygen. So here's my mole ratio from the balanced equation that's going to let me switch compounds, let me go from talking about water to talking about oxygen. If I stop right now, my answer will be in moles of oxygen, but they actually asked me for grams of oxygen. That's okay, right? I can do that. I take these units, I bring them down again, and I go back up here to my list and I say, do I want to change it to a different compound? No, I want oxygen, I'm good. What I want to do is change it to grams. Now I put in my numbers. This is super important, guys. This is where a lot of people make a mistake. Remember that our first conversion was 1 mole of something weighs the number from the periodic table. Okay, so make sure that you're using a 1 when you're looking up the mass because you're looking up the mass of 1. Do not ever bring those numbers down. You only bring down the words. If you bring the numbers down, you just undid all of the work that you did previously. Okay, so only bring down the words. So now I'm going to plug in, just like before, all the numbers into the calculator. I'm going to multiply across the top I'm going to divide by the bottom. I'm going to write down my answer from the calculator. Okay, it gave me 6,112. Okay, I need sig figs though. My sig figs are 1, 2, 3. So that means it's going to be 6,110-ish. Okay, so again, we look to the neighbor to decide, is it closer to 110 or closer to 120? Well, it's closer to 110. So I'm going to say 6,110, no decimal, grams of oxygen. This has 3 sig figs. Okay, we're not going to make it 611. That would be wrong. It's 6,110. So this one would be our best answer. You also could, if it makes you feel better, put it into scientific notation. But if you do that, it still has to have the same 3 sig figs. So both of these would give you full credit because they both have sig figs and units on the answers. Okay, so now what? Well, what we always do, we practice. There are 2 things for you to work on today. Please do them in order because there's a reason for it. There's always a method to my madness. So the first thing that everybody should be doing, right, is the 32.1 introducing mole ratios. This is a quick review of the first part of the lecture. It is the short and sweet, just doing mole ratios. Okay. You do have to show all of your work. That means all steps with units fully labeled. If you want to do it on paper, you totally can, and then take pictures and insert those into the document with the questions. I love when you guys do that. Or if that's too hard for you and you just want to upload one big PDF, you know what? That's okay too. It's not the way I'd prefer, but I will totally take it. Or you can just put them into the document. I did set up the little tables for you since these are all the same short little guys. So I did put them in there so you could just type in them if you wanted to. This is classwork. The date that it's due is based on the day that you have class. This should be done before you leave the room. This will be very easy to do because this lecture is only taking about 25 minutes and you have an hour left. So you have tons of time. So do this one first, turn it in. Then you start and maybe finish, just depending on how fast you are, the 32.2, which is where we add in that last step of changing moles to grams at the end. Okay, so this one has 2 and 3 step problems. So it's a little bit more challenging. This one over here is just 2 steps. Okay. But again, don't worry about whether or not it's 2 or 3 steps when you start the problem. Just set it up the way we know how to set it up and go through the motions and it will get you there. Okay. One more thing before I sign off here, which is make note of the open office hours. They're a little bit later this week. They're 1 to 3 because I have meetings in the morning. And if you haven't already checked out the agenda, make sure you do that because on the Thursday and Friday classes, the first thing we're going to do is a little, you can call it a quiz, you can call it an assessment, I don't care what you call it, on empirical and molecular formula. We're not doing that today because we hadn't had office hours yet, and I wanted to make sure that we had office hours so that you could ask questions if you had questions. So when we come to class on Thursday or Friday, depending on your day, the first 30 minutes of class, I will open up this little quiz. You will do it. Then I'm going to close it, and then we'll do the second half of the week, the second lecture and assignment. So please, please make sure that if you are not sure about stuff from last week, you show up to office hours and get some help. You can ask about anything from last week or anything from this lecture, but make sure that you're proactive and come and get some help if you need help. All right, so that's it for today. I'm going to sign off. You are now going to jump into Google Classroom and take care of reviewing the lecture that we just did with 32.1 and then really stretching yourself to practice with 32.2.